Do you remember properly? Am I audible? I think I am audible. All right. So we were solving this one mathematical part we did in the previous lecture, if you remember. This part, mu and all these things that we solved for the normal distribution, right? So do you have any doubt in this one that we solved? All right. So now what we are going to do, we are going to apply the R programming, R code here. Okay. And this is the R code for your machine problem. Okay. So this was the data that we had. Okay. In this data set, we have the observations of two machines, right? Where the data set that was coming from the two machines means what was this data set? This data set was the 20 bearing diameters measurement of that coming from the two different machines. But problem was that we didn't know that which line or which diameter or which observations are coming from which machine. All right. So in that case, if we were saying that both of them, whatever the measurement of the diameter of bearings from both machines are following the normal distribution with the mean mu1, mu2 respectively, and variance is same for both of them. Means we are saying the bearing diameters, that is say x1, that follows the normal distribution with mean mu1 and variance sigma square, and x2, that is the bearings diameter from machine 2, and again it is following the normal distribution with mean mu2 and variance sigma square. Means mean is different but variance is same for both of them. At that time we want to compute the estimate of mu and sigma square, mu1 and mu2 and sigma square. But problem is here that we don't know which observations are coming from which machine. So how will you find out the average length here, mu1 and mu2 and variance sigma square at that time, right? Are you getting my point, what I'm trying to say? If you don't know which observations are coming from which machine, so how will you find out the average bearings diameter for a first machine or second machine? And after that thing is that because we have the observations, they are going to be mixed here. Okay, both of observations are mixing, right? They already mixed. So here we are assuming that both of them are going to be mixed with the proportion pi. Okay, both of them are now a joint distribution, mixture of normal distribution. Do you know about the mixture of the mixture distributions? Do you have idea about that? What is the mixture of the distribution? Mixture of the distribution means that if you have the two populations, okay, and they are going to follow the same distribution, and you are going to mix both of them observations, so the distribution that will follow now for that new observations, that will be called as the mixture distribution of both populations. Like that we have the assumption in our daily life situation, we have the assumptions that the marks of the students are normally distributed. Yes or no? So in that one, if I'm going to say that the marks of any particular class, say BSc first year, BSc first semester, okay, their marks of any particular subject, we are going to talk about the mathematics. Okay, say in the math, whatever the marks they are getting the marks x1, x2 up to xn. These are their marks, and I'm going to say that they are going to follow normal distribution. If they will follow the normal distribution, definitely some mean will be there, and mean in the normal distribution we denote by the mu. So I'm saying that this time mean is mu1. Are you getting my point? What I'm trying to say? And variance is sigma square. Variance can be differ. Okay, variance can be differ or variance can be same. But we are assuming variance is same for both of them. And in the BSc third semester, again in the mathematics, the marks of the students follows the again normal distribution, and the marks is y1, y2 up to ym. These are the number of marks of the students. Okay, and this time it follows the normal distributions, mu2 and sigma square. Is it possible or not? Because we are saying that the marks always normally distributed, right? So if the marks is normally distributed, so the BSc first semester students' marks will also follow the if follows the normal distribution, then the marks of the third semester students will also follow the normal distribution, right? If I'm going to mix both of these marks and my new data set that I'm going to prepare, that is x1, x2 up to xn and y1, y2 up to ym. This is my new data set. All right, the size of the data set is n plus m. This is my size of data set. So which distribution it will follow? Normal? Yes or no? Definitely it will follow the normal distribution. What will be the parameter? And what will be the that one? Basically the PDF form. What will be the form of the PDF? So at that time, what we do, we will multiply with the proportion, some proportion. Sometimes we say it pi, sometimes we say it small p, and we just add it in that manner that pi is equals to pi naught is equals to 1 minus pi 1. Means pi naught plus pi 1, that is basically the probabilities, is total probability should be 1. Means the number of the marks these students is following the normal distribution with mean mu1 and sigma square. The probability of that one is pi naught, and these marks follows the normal distribution with mean mu2 and variance sigma square. The probability of that one is pi 1. Okay, so we introduce the proportion in that manner. Okay, so if you remember when we developed the model in the previous class, what we did? We introduced the pi there as a, we introduce probability of z equals to 1, means it is coming from the first population. So that was pi I, and it was coming from the second population. The diameter's value is coming from the second population, that was 1 minus pi I. That we given in the previous lecture, if you remember this thing. This thing happened, right? So that's how we need to introduce this thing. And after that, when we just introduce the PDF mixture density, how we introduce the mixture density after this? We introduce the mixture density, that was F. We introduce Fy mu sigma square, that was basically pi I, or probability is equals to 1 into the first density of xi, plus 1 minus pi I, that probability that z is going to take the value 2, means the observations that we have here, these observations are coming from the second machine. The probability of that one is 1 minus pi I into the probability density function of that one. Okay. That was the mixture density. This is called as the mixture density. So that's how you can develop the different distributions. Okay. That's how they develop different distributions. Okay. So what they do basically most of the time, if I just show you one distribution, it will be there definitely. Google Scholar. So X. So this is the X gamma distribution that was developed in that one 2016. Okay. So what they did in this distribution, they just they took that one exponential distribution and gamma distribution. Okay. So this is the finite mixture distribution. Okay. They were getting the mixture of the distributions. Okay. Please see here. So what they did, they said if pi I fix means pi 1, pi 2, pi k denotes the mixing proportion. So you can introduce more than two proportions there. Means you can find out the mixture of more than two distributions also. Means I can include the BSc third semester, BSc fourth semester, BSc second semester. All those I will add, and then with respect to them I will introduce the pi 1, pi 2, pi 3 mixing proportion, and then I can take the summation of all of them, those density, and it will provide me the new mixture distribution. Are you able to see that? Should I increase? Okay. Are you able to see it? So that's how they are going to mix the distribution. So it will provide them the new distribution here. So what they did here, so in f1x, they assume that it follows the exponential distribution with parameter theta, and f2x, the second density, is following the gamma distribution with scale parameter theta, the same parameter, but the same parameter they just restricted at 3. Okay, we take the alpha beta, na? We take the distribution parameters of gamma distribution alpha beta. So instead of that one, they just took the 3 and theta. And they introduced the proportion in this manner that pi 1's value they took theta upon 1 plus theta, and pi 2 they introduced as the 1 minus pi, means 1 minus theta upon 1 plus theta. They introduced in that manner. After that, when they combined both of them, okay, when they combined, they got this PDF. Do you know how? What they did? Are you getting that one? Or should I explain? So I'm just telling you what they did. Just take it this here. Are you able to see this? So what they did, they were saying that population was following the same exponential distribution. X was following the exponential distribution with parameter theta. Okay. So what the density they took here, they took the density of fx, f1x. the first population's density. They took as theta into e raised to the power minus theta x. Okay. After that, they said that f2x, the second population, means if we just say the marks of the third semester students, it was follows the gamma distribution with parameter 3 and theta. What is the meaning of this one? The density they took theta raised to the power 3 upon gamma 3, sorry, gamma 2, because at the instead of beta 3, they took the beta equals to 3. Instead of beta, they took beta equals to 3. And for alpha, they took theta. So it will be e raised to the power minus alpha. Alpha equals to theta. They took alpha equals to theta and beta equals to 3. So it will be e raised to the power minus alpha x. So what it will becomes? Theta x. Instead of alpha, they took theta. What they did? What is the PDF of gamma distribution? PDF of gamma distribution fx. Alpha raised to the power beta divided by gamma beta into e raised to the power minus alpha x into x raised to the power beta minus 1. This is the PDF of gamma distribution. Yes or no? This is. So now I am saying that instead of alpha, put theta, and instead of beta, put 3. So if I am going to put alpha, so instead of alpha, I am putting 3, sorry, theta, and instead of beta, I am putting 3. So here, it will be gamma 3. Okay. And then e raised to the power minus theta x and x raised to the power 2. Right. Now what I am going to do that, what they did, they said, I have these two probabilities. So I am going to combine the marks of both classes. So again, it should follow some distribution. And what distribution it will be? It should be the combination of both distribution. When I'm going to merge the marks, I'm going to combine all the marks in one data set and show it as a one single data set. So whatever the distribution will comes, that should come as the mixture of both of them, because I'm going to mix the marks. Yes or no? So how I'm going to mix them? I'm going to mix them with the proportion pi 1 equals to theta upon 1 plus theta. So this parameter I just took common. So some common value, some common parameter should be there when you are going to mix the distribution. Okay, that is the standard way to provide the mixture, and that proportion should be in the form that when I'm going to introduce the pi 2, that should be 1 minus pi 1, because it will imply that pi 1 plus pi 2 should be equals to 1, because total probability should be 1. Total probability should be 1, right? So if I'm going to going to provide the mixture of two distribution, at that time I have only two mixture proportions, pi 1 and pi 2, right? So both of them should be equals to 1. If I'm going to include one more density, f3x, if I'm going to include here f3x, so at that time I need to introduce the pi 3, and that will imply that pi 1 pi plus pi 2 plus pi 3 should be 1. That will be our mixing proportion. So what I'm going to do, what will be my pi 2 here? 1 minus theta upon 1 plus theta. So 1 plus theta will multiply in 1. So 1 upon 1 plus theta. So what I will do, now my density will be theta upon 1 plus theta into the density of exponential, that is theta into e raised to the power minus theta x. Okay. That will be my first density, and second density will be 1 upon 1 plus theta, okay, and into theta raised to the power 3. That will be factorial 2. So means 2 into e raised to the power minus theta x into x square. Right. After that, I need to only simplify this one. When you will simplify this equation, you will get this PDF. Because what will happen? It will be theta square when you will multiply inside. So it will be theta square into e raised to the power minus theta x divided by 1 plus theta plus just multiply inside. So it will be 1 upon 2 into 1 plus theta into theta cube into e raised to the power minus theta x plus x square, right? Theta square will be common. Theta square you can take common because this is theta square, this is theta cube, and 1 plus theta also in the denominator you can take common. So what it will be? It will be theta square upon 1 plus theta, and inside the bracket e raised to the power minus theta x also you can take common. Okay. So what it will remain? So this term will be 1, will becomes 1. So 1 plus what it will be? Theta. So it is in the multiplication, not in the plus. So theta into x square divided by 2 and into e raised to the power minus theta x. The same distribution you are getting from here. Okay. So this will becomes your new distribution. So we don't have the name of for this distribution. So what did they just give the name from their side, x gamma. Okay, they took the x from the exponential and gamma as it is. So they give the new name to this distribution as the x gamma distribution. So that's how they drive new distributions. Okay. Huh? One common parameter we should have. No. They just took from their self. If you just what they did they just took the 3. If you will take theta equals to 1, okay, I think in theta equals to 1 or theta equals to 2, it will becomes the Lindley distribution. It is a very famous distribution right now. It was developed in the 1958. So if I am not wrong, give me a second. I can show you if I have the paper of that one. Okay, Lindley distribution. So let me check if I have this PDF. Yeah. So if you just see this distribution, okay, this distribution came in the 2000, sorry, 1958. Are you able to see this one? Equation 1. Compare this equation. Compare this equation with this. What is the difference you are finding here? 2. Instead of 2, they took the 1. So what they did, they took the beta equals to 1. Then only this theta will remove, na 1 minus 1, 0. Theta raised to the power 0. Right? So Sorry, theta equals to 2, that 2. Theta equals to 2. Not theta, sorry, beta. Beta equals to 2, they took here. So then what it will become? It will become here in this PDF. It will become theta square gamma 2, what it will be the gamma 2? 1 factorial, that will be 1 e raised to the power minus theta x and x raised to the power 1, right? So it will be theta square then. So theta is, because it is theta square, and when you are going to take this proportion, so this will also theta square, this will also theta square, so theta square will come out. So 1 plus x square into e raised to the power minus theta x. So you can take the different values of beta here and you can make the new distributions with this combination. You can make more than 100 distributions here right now. That's how they publish the distribution paper. Okay, so that's the same thing we have done here. Okay, so what we did, we just took the mixture of these distribution of two normal densities. All right, and problem is that here in this one, in this example of the x gamma distribution that I took here, we knew the value of pi. We knew the value of pi. What was the mixing proportion? That we took as the theta upon 1 plus theta. So whatever the value of theta you will take, you will automatically get the value of pi 1 and pi 2. Right? Whatever the value of theta you will take, corresponding to that value of theta, you will automatically find the value of pi. Right? But we do not have the value of pi here in our one. So what is the problem we have? We need to estimate the pi. We have to estimate the mu1, we have to estimate the mu2, and we have to estimate the sigma. All three we need to estimate. Okay. So in that one, what we are going to do? So we have machine 1, machine 2, both of them are following the normal distribution with mean mu1, mu2, and mixing, with the same variance, sigma square. And in that one, pi is the mixing proportion. So what we are going to do here, we are going to store the data set in the y. Okay. So this is our data set. And we need the number of observations here that will be stored in the n. Okay. So here we are going to print y. That you don't need that. You can either do it or directly you just leave it. Okay. So number of observations in n that we are checking, that is 20. And after that we are going to plot the histogram of our given data set. Okay. In that one, y is the data set in the command, breaks equals to 10. Okay. And in the title should be histogram of the bearings diameter, and on x-axis diameters, and column will be the light bulbs and the border is black. So that is, we are going to run it. So we got the frequency. Okay. So around 10 bulbs we have that are from between 2 to 2.5. Okay. And we have 10 bulbs here that are between 4.5 to 5.5. Okay. And let's plot to show the individual observation. For that one, command is UI. So these are the roughly observations. Okay, where they are having the observations. Okay, these small lines here. Okay. So now after that, we are going to start with some initial value. Okay, we need to give the initial guess from our side. And we are free to give it. But condition is again the same, that value should be in between the limit. Like mu lies between minus infinity to infinity. So value of mu1 and mu2 should be lies in that limit, and the variance can be lies between 0 to infinity only. It cannot lie in the minus sign. So it should be between minus, sorry, 0 to infinity. So positive observations. And pi, the problem is that with the pi, it lies between 0 to 1 because it's a proportion. So value should be lies between that limit only. So that's why what we are doing, we are giving 0.5 because we are saying that they have the equal probability that we are assuming. And 2.5 we are giving because most of the observations are lying between 2 to 2.5. And for the mu2 we are giving 4.5 because most of the observations lie between 4.5 to 5.5. Okay. And sigma we are giving 0.5 from our side. Okay. So sigma basically that should be the square to get the variance. Okay. So now we are going to check the observations here. These are the observations that we are going to provide. Okay. After this, we are going to define the normal density function here. Okay. That is 1 upon square root of 2 pi into sigma square. And sigma square we are going to store in the sigma 2 current. Okay. And e raised to the power minus y minus mu whole square divided by 2 sigma square. And we are going to make it a function of y, mu and sigma square. So whatever the y, mu and sigma square we will provide, so it should provide the value corresponding to that. Okay, so this is the function that we are going to define. So now we will check the density at the pi 2.5, 2.5 and 0.5. Mean 2.5 and variance 2.5, 0.25 and the observation is 2.1. What will be the our PDF? So this is the value of our PDF for the given value 2.1, 2.5 and 0.25. 0.25 is the variance, 2.5 is the mean and 2.1 is the observation of y. Okay. So now after that we will go for the E step. In the E step, we provided the formula of gamma. Sorry. This one. So formula of gamma we provided here. It was this. Pi t phi yi mu 1 t sigma square divided by pi t sigma phi of yi mu 1 at the iteration t and sigma square at the iteration t plus 1 minus pi at the iteration t and phi y mu 2 at the iteration t and sigma square at the iteration t. Are you getting this? What we are, this is basically pi t is the proportion value and phi is basically the normal density function with mean mu1 and sigma. And because here in the EM algorithm is like a MH algorithm and the gift sampler where we have the iteration. So what we do, like a gift sampler, what we do, we just we just give the initial value at the zero iteration. Okay. At zero iteration, sorry, at the zero iteration, we will give the initial guess, initial values of parameters. Okay. So whatever the value we will give in the initial stage, that will be at the zero iteration. After that, what we will do, we will put those values in this formula. So it will be mu1 0 sigma 0 square mu1 0 square. Okay. So yes, mu1 0 square, mu1 0 sigma 0 square, mu2 0 and sigma 0 square and here pi 0. So whatever the value we gave here in the R code, this value, these initial values. Okay. So when you will put these values with respect to your given data set. for this data set, you will put here, you use this data set and this density function, and you will put those values in this density function here. Okay, and value of pi, sigma square, and mu. So this will provide you the probability. Yes or no? Correct. And then you can estimate the value of mu and mu1, mu2, and sigma square and pi from here. Yes or no? So what you will do, basically, I just tell you. We will put the values here. Okay. We will put the values here. And this is the density function, basically, phi. We are not writing the complete density function. Instead of writing the complete density function, we are writing the phi. Okay. Instead of writing the complete density function, we are writing phi only. That is, will be the function of y, mu, and sigma square. Are you getting this point? So I am not completely solving this one. I am leaving it in the form of the function, density function. Okay, function of y, mu, and sigma square. So I will get the value of gamma 1 from here. I will get the value of gamma 1. Yes or no? When I will put all the initial gas here, all the values are known. So I will get one value of the gamma 1. And what is gamma 1? Gamma I1 is the equals to 1 minus gamma I2, or vice versa. So I will get the value of gamma I2 from here. What? So what we are doing here, this is the E step, expectation. What is the expectation? What is this basically? Gamma I1t. Gamma I1t is the basically the expectation that it is coming from the machine 1. Okay. Gamma I2t is basically expectation that it is coming from the machine 2. So first we are getting this expectation, estimated expectation here. After that, what we will do, and these we call as the responsibility. Okay. And after that, what we do, after getting this one, these values, we will try to maximize this one. We will try to maximize this expectation. Okay. So when we try to maximize this one by again and again iteration, so in the last we got the value of the estimated parameters where they will converge, where they will get the maximum expectation, that it is coming from the machine 1 and it is coming from the machine 2. What is the highest maximum expectation of that one? If you just see here in the previous example that we solved for the binomial, the coin 1 and coin 2, what we did, we started with the theta. Okay. So what we did, we just find out the estimated value of theta 1, theta A and theta B, the probability of the success. All right. In that one, what we were trying to do, we find out the expectation here. Okay. We found out the expectation that it is coming from the that particular coin. Okay. Coin A or coin B, if you remember. So we find out the gamma 1A, the expectation that when we toss the coin, so whatever the number of heads we got from the coin 1 or coin A. All right. So what was the expectation of that one? 0.449. So what it for the given current estimates, there are 44.9% of the probability that the experiment 1 use the coin A, and when you are going to subtract with the 1, so it will come as the 55.1, means 0.551. That is the percentage basically that it comes from the coin B. Okay, that is the basically the probability that we are finding that it is coming from the coin A or coin B. Okay, this is the probability, and we are going to maximize this probability. Okay, so here we are going to find out this gamma 1 I with the initial guess, and then we try to maximize this one. Okay, this is for the, yeah. And after that, mixing proportion that we took with after solving the equation, we find out the formula of the mixing proportion, that was n1 upon n. Okay, n1 is the sample size of the first, that it is coming from the first observation, first machine, and n2 is the size of the observation that they are coming from the second population. Okay, and this is the weighted mean. Okay, where we are going to include the probability that it is coming from the first machine or the second machine. Okay, and the variance also the weighted variance, or the you can say the pooled variance here, where again you are going to include the probability that it is coming from the first machine or the second machine. Okay, so what we are going to do here, we have the gamma I1, that is the probability that it is yi is coming from the machine 1, and gamma I2 is that probability equals to the probability that it is machine 2 is used for the given yi. Alright. So the formula that we had the formula pi into pi of yi mu1 sigma square divided by pi into pi yi mu1 sigma square plus 1 minus pi into phi y for with the mu2 and sigma square. This formula that we have used here. Okay, this formula. So we are writing this formula to find out the values of gamma I. Okay, so we have the two density functions. So we are going to define the density function under both machines here in the each step. So we are going to define the each step as the function of y, observations, value of pi, mu1's value, mu2's value, and the sigma square's value. This is the function of how many values? 1, 2, 3, 4, 5. Okay, so we are giving the five variables here. So each step is the function of 5 variables. So in that one, we need to define the density function for both machines, and we are saying both are following the normal distribution. So normal PDF we already define here. Okay, normal underscore PDF. That is the function of y mu and sigma square. So instead of y mu and sigma square, what we will do? We will put y mu1's value and sigma square's value. Okay, and under second machine F2, in the F2 we will define the normal distribution with the value y remain as it is. Instead of the mu1, it will be the mu2, and sigma square will remain as it is. Okay, so after that we will get the responsibility for the machine 1 gamma 1. So what will be the gamma 1 now? In this formula, we need to put the PDF of gamma distribution with mean mu1, okay, in the numerator and denominator, and the gamma normal distribution with parameter mu2, right? That we already defined in the f1 and f2, right? So what it will be your gamma function? Pi values into f1, that is your first density under the first machine, pi into pi's value into f1, 1 minus pi's value into f2. F2 is the PDF under the second machine. And what is the responsibility for the machine 2? That will be gamma 2 equals to 1 minus gamma 1. Okay, so it should return as the gamma's value, gamma 1, gamma 2 value, and f1 and f2 value. It should return us. All right, so now we will run it. Okay, after that, what we need to do? We need to go for the M step. In the M step, what we need? We need the weights that is n1, that is the sum of gamma 1 I, n2 is the sum of gamma I2, pi nu, that will be the n1 upon n, and mu 1's value is the sum of the gamma I into yi divided by n1 from this formula. From this formula. Okay. And mu2 is the sum of gamma I2 into yi divided by n2. And sigma square formula that we are going to use, that is the sum of gamma I1 into yi minus mu1 square plus sum of gamma I2 into yi minus mu2 square divided by n. So we need to introduce it as a function of gamma 1 and gamma 2. Whatever the value of gamma 1 and gamma 2 we will get from here, from the E step, we will keep in the M step. It is a little bit tricky, but you need to be focused here. So in that one, we will store the sum of the gamma values, okay, for each iteration. All right, for and n2, that is the sum of gamma 2, and we will update the mixing proportion with the pi nu equals to n1 upon length of y, and we will update the means with the formula sum of gamma 1 into y divided by n1, sum of gamma 2 into y divided by n2, and we will update the our pooled variance, that will be sigma 2 nu under the sigma nu, that will be the sum of gamma 1 into y minus mu 1 mu under is called nu, that is the updated mean square plus sum of gamma into y minus mu 2 updated mu divided by the length of y, and new sigma will be, that is the your standard deviation will be the square root of the new variance, and it should return us the p value, mu1 mu2's value, sigma value, and n1 and n2 values, the m step. So this is the function that we build here. That is done. Okay, now the observed data likelihood, we need to provide the likelihood function here. So what is the likelihood? Product over the range of I will go to 1 to n for the given data set. We are assuming all the data observations are computed, so it will be complete data set here. So we will introduce it as the function of pi's value, mu1 mu2 values, and sigma values. All right, that will be the mixture density, okay, that I defined here like this one, the likelihood of this mixture density. Okay, so this is the mixture density. Now we are going to check for the first likelihood. For first step, what are the observations that we have? So in the first step, we are going to check the values of y and pi's current value, and mu1's, mu2, and sigma 2's current value. Okay, we will check here. These are the values of the density function for the each value of y. We have the 20 values of y. So for each value of y, we have the values of gamma 1, gamma 2, f1 and f2 here. Okay. These are the values of your both density functions and respective gamma. Okay. So here we made a table. Okay. For each one, we made the table here. Showed in the table. Now first m step, we will check what is the first m step it is providing us. So after maximizing, so it is providing us the pi's value, n1's value is 8.99. Okay, the effective sample size of first coming from the first machine, that should be 8.99, and effective size that coming from the second machine, that should be 11. Okay, and pi should be 0.44, pi 1, and pi 2 should be 1 minus 0.449. Okay, or you can say 0.45. And updated mean will be 2.17. What the mean initially we took here? 2.5. Instead of 2.5, when we update the first iteration, it came as the 2.17, and the updated mean for mu2, it comes as 4.91. Initially we took at the 4.5, right? And the updated sigma is 0.024. Okay, and we took as the 0.5. Okay. Oh, sorry, it is 0.15 because this is the variance. We took the standard deviation 0.5 and it came as the 0.15. Okay, so this is our after first iteration. It happens. Now these values will be used as the initial guess again. They will replicate our initial guess. And then we will go for the further part. Okay, so now we are going to take the 100 iteration and the convergence tolerance is e raised to the power minus 6, 1 into e raised to the power minus 0.6, and we will create the matrix of the data that here it should provide us the iterations and all the 100 iterations and value of pi, value of mu1, mu2, sigma 2, that is the basically sigma 2 is the standard deviation, and log likelihood value. All right, for each iteration it should provide us. So here we are giving them the empty numeric vector. Okay, all the values are the numeric. All right, so for that one we are going to run the iteration here, 1 to up to 100. And in that one, in each step, we are going to calculate y, pi's value, and mu's value, mu1, mu2's value, and sigma value. All right. And then we are going to use in the m step the y, gamma 1 and gamma 2's value, and the log likelihood we already defined here. And then we are going to store the results. Okay. In the uh, iteration pi, mu1, mu2, sigma, and sigma 2, and log likelihood, and we are going to call the values here. After that we are going to check the convergence, whether it is going to be converged or not. So we are going to check the difference, absolute difference of pi's current value and pi's estimated value, means the initial gets that we are using. Okay, we already estimated, and by using this value, what we are going to estimate the next one, and we are going to check the difference of all of those values for pi, mu1, mu2, and sigma. Okay, so if the difference for any of these is less than the tolerance limit that we took initially, okay, 1 e minus raised to the power minus 6, so it should stop, otherwise it should again break it and again start the iteration. Okay, so this is the basically estimated values here. So now we will try this one. Updated sigma up to here, right? So these are the values for each iteration. Okay, iteration 1, iteration 2, iteration 3. So converge we already reached in iteration 3. So it is not going for the 100 because we already have the convergence in the third iteration, because we are saying that if it is less than, the difference is less than the tolerance limit, so it should break here. Otherwise it should continue. So we already got the convergence at the third iteration. So at the third iteration, we got the value of pi, that is 0.45. Mu1's value is 2.177. Mu2's value is 4.91. Sigma's value is 0.156 and sigma square's value is 0.024 and log likelihood value is minus 5. Okay. So this is the difference here. And these are the values after the iteration. Now we will check. the iteration table. This is the each iteration, the values we just store in the table, and we check the that one convergence plot. So this is the convergence plot for the mu1. Okay, so initial value was 2.17 at first iteration, and the second iteration it was 2.1778, and the third iteration it was remaining same. Okay, so how we just get the values from the result? In the result we had the values here. Okay, we store the values in the results. Okay, and we extract the value from the results with the dollar sign. I hope you know that how to extract the value from any data set. Do you know that? By the dollar sign and the variable that you want to extract, and type B. Type B means line and dot both, and the PCH is 19 means the size, okay, width of the line. How much, and the dot, what should be the size of the dot? That is, I'm taking the 19. If I will increase it, so dot will be becomes more big. All right, and the x it axis it should be iteration, and y axis it should be the expression of means value of mu1, and the title of that one convergence of the mu1. All right, now check for the similarly we will check for the mu2. So it's we started with the 4.91 in the first iteration, and then we got 4.91818. All right, and in the third iteration we were getting the same, and for the sigma again it is similar in that manner, and we will check for the log likelihood. What is the how the log likelihood values are varied. So in the each iteration, whatever the values of the log likelihood, it is showing here. All right. So you can leave it here. Others are not for you. The other part of the code. Okay. So this is the basically your R code for your two machine problems. Now we will discuss about that one under the censoring scheme. Okay. So do you remember the type 1 censoring and type 2 censoring? Huh? Do you remember what was the type 1 censoring? Particular? Yes. So means basically when you have the any experiment, you are running any experiment or you conducting any experiment at that time, if the experiment is going to be take a lot of time, like in the experiment of the bulb, what is the failure time of the bulb, or if you are taking any patients are going to take any treatment or anything, any other studies like that. So at that time, it will be time consuming more than the other things. It is most of the time consuming. So what we do in such experiments, we just restrict the time. We are not worried about the observed data, means how many observations we will observe completely. We are worrying about the time. Okay. So we says that after this particular time, we will stop our experiment. Okay. Means like there, suppose we conduct an experiment and up to the fixed time, that is c greater than 0, that is called as the sensor time. So if a unit fails before or at the time c, we call it as the exact failure time or exact failure observation. Or if any observation is going to survive beyond this given time c, okay, that will be called as the censored observation. Okay, and because that is not observed completely. All right, so this is called as the type 1 censoring. Okay, type 1 censoring. Okay, so here it is assume it like this. If xi denotes the true lifetime of the ith unit. Okay, lifetime of ith unit. All right. So in that one, so under the type 1 censoring, the observed data are basically defined as the yi equals to the minimum between xi and c, because x is also a time and c is the also a time. So whatever the minimum observation you have in between xi and c, so that will be your observed data. Other than that, whatever the observation you will get, all of them are the censored. All right. So uh, here yi will be defined as the observed data set, okay, from the given all xi's, and c will be the censoring time for the fixed, and we define it as with the indicator function like delta I, that is basically between 1 and 0. Okay, between 1 and 0. So we say it takes the value 1 if xi's are less than or equals to c. Means we observe the failure time. Observed failure time. And it should take 0 when xi is greater than c. Strictly greater than c. Okay. So it will basically right censored. Okay, it should be right censored at that time. So observed data will we define in such manner that y1 delta 1, okay, or y2 delta 2 up to yn delta n. Means delta's value will vary with respect to the y, okay, whether they are observed or not. All right. So in that one, uh, we just take a one real life example that suppose in a factory that manufactures the electric bulb, so the engineer wants to estimate the lifetime distribution of the bulb. So in a test, we run the to running a test, we just put the n bulbs on testing, and the experiment stop after the fixed time, say c, that we mentioned here. Before this time c, we are going to stop the experiment. So if the bulbs fail before time c, the failure time is recorded. Exactly, if it is still working, the bulbs are still working at the time c, so we only know that the lifetime is greater than c. Okay, so if bulbs are observing, still running, so we know that they are working up to the time c, and when they are going to be fail after this particular time c, when they are going to be fail, we don't know. All right, so this is the incomplete data for all of us. So it will be like this. So here we just take the example of the exponential distribution. Okay, this is the easiest example. So in that one, suppose xi follows the exponential distribution with parameter lambda. So I goes to 1 to up to n. All right. So corresponding probability density function will be, what will be the corresponding density function? Lambda into e raised to the power minus lambda xi. Xi is greater than 0 and lambda is greater than 0. All right. Here we need the survival function also. Okay. Here we need a survival function. So what is the survival function of x of exponential distribution? E raised to the power minus lambda x. Right. And corresponding mean is, what is the mean for this density function? 1 upon lambda, right? So Now, thing is that why we need the EM algorithm here. Okay. So exact failure types of the sensor data observations is missing. All right. We have the observations where we have the data for the only those observations, the exact failure time only for those observations that was failed before the type C. But we do not have the information, complete information, or you should say the exact information about those bulbs or those units which was running at the time C when we terminate the experiment. We do not know the exact information. All right. So in that case, what happened? The data will be incomplete. In that situation, data will be incomplete. Right or not? Right. So EM in the EM algorithm, we will use the iterative method. Okay. So what we do, we just compute the conditional expectation for the complete data log likelihood for the given observed data and the current parameters value, and then we maximize this expected complete data log likelihood with respect to the parameter and try to find out the value of the lambda here. Okay, so in that one, what is the likelihood function? What will be the likelihood function of the this one exponential distribution? If time's up, please let me know. I don't know what is that. So it will be I goes to 1 to n lambda into e raised to the power minus lambda xi, right? So it will be lambda raised to the power n into e raised to the power minus summation over the range of I goes to 1 to n lambda xi, right? Take the log, take log on both sides here. So what you will get, it will be for the complete data set. So it will be lambda given x curve. So it will be log of n log lambda, right? Then minus lambda summation over the range of I goes to 1 to n xi, right? That will be your log likelihood function. Now just come for the each step here. Okay. In that one, we need to find out the estimates of lambda for each iteration. All right. So we need to find out the lambda t for tth iteration. And so in that one, what we will compute the q, that is the conditional expectation of the lambda for the given value of the lambda at iteration t. All right. So lambda t is basically the current value of the lambda at the tth iteration, and we need to find out for the t plus 1th iteration. Lambda t we already have. We need to find out for the t plus 1, right? So what it will be? It will be the expected value of complete log likelihood function of lambda given. In the d we have the observation, okay, and lambda t. In the d you have the all these observations x1 x2 xn. All right. So what is your log likelihood function? Log likelihood function is n log lambda minus n summation I goes to 1 to n xi. So you need to take the expectation on this one, right? So when you will apply the expectation on this with respect to the lambda, so what you will have? So with respect to the x, so what will happen? What will be the expression you will get? N, sorry, n log lambda minus minus into expectation of xi, sorry, summation I goes to 1 to n xi for the given observations, observed data set and value lambda t. All right. So now just take the expectation. All right. But now problem is that you do not have the complete observations. All the observations are not observed here. That you have summation over I goes to 1 to n xi, that you have all those observations are not observed one. Few of them are incomplete, right? So what you need to do? You need to divide it into two parts. Summation over the range of I, okay, with semicolon delta I should be 1, means the observations should be observed. Okay, delta I we denote here, define here. Delta I should take the value 1. If xi is less than equals to c, means observations were observed before time, and delta I should take the value 0 if observations were censored. Okay, so now we need to define it in this one. Xi plus summation over the range of I, semicolon, delta I should be 0 of xi. All right. So that should be the observation, your xi. Now you will split it into two parts. Okay. So after that, now take the expectation. Okay. So for uncensored observation, we took that xi was equals to yi, correct? Right. And in that case, then expected value of xi for single value, we are not taking for the summation, xi for the given observed observation and given lambda's value at the tth iteration will be equals to yi. So basically, we need to find out the expectation for the censored observation. All right. So it will be like this. Here you need to include one thing in this one. D observations, then you need to include delta I is equals to 1, means it is observed, and it is D observes are basically yi. Okay. So then it will becomes yi. Now you need to find out for the censored data. You need to find out for the censored observations, that is basically expected value of xi given that xi is greater than c for those observations and at the given value of lambda at the tth iteration. All right. So for the exponential distribution follows the memory less property. Yes or no? So because of less property, xi, given that xi is greater than c, will be equals to c plus z under the distribution property with where z follows the exponential distribution with parameter value lambda t. So we are not interested in the previous value. Okay, what are the previous values of x? We are interested at the values of c. What are the values of x we had at the c? Okay, so what will be the value at c at that time? It will remain c. Means basically what happen? If you have x1, x2 up to xn observations are there and they are going to be fail. Oh, sorry. Our observations were failed before time c. Okay, were failed before time c. So what will happen? So x1, x2 up to xr. Those observations will be considered as the complete observations and xr plus 1, xr plus 2 up to xn. The remaining observations, all of them were greater than c, but you don't know the exact value of those. What is the value of xr plus 1? What is the value of xr plus 2? What is the value of xn? That you don't know, right? But you know that they were at least c. They had the value at least c. Means they were in the working condition, na? Yes or no? So you will call it as you will assume that they have the time c. All of them are equals to c. So that's why we are going to consider that c plus z. Okay. So here, what will be the expectation at that time? So the expectation of xi, given that xi is greater than c for lambda t, it will be c plus 1 upon lambda t. Okay. C plus 1 upon lambda t. Because we do not have the expected time after that, but we have the time that it was c. So that's why we are going to add c here. All right. And if number of failures, how many number of failures we will have? How many number of failures we will have here? That are we are saying. These are. What is the number of these are? How will you find out that one? That r will be summation of delta I. Yes or no? At I goes to 1 to n. If n observations are there. Yes or no? Are you getting this point? Why it will be summation delta I? Are you getting or not? See what we were saying here in this one. Lambda I should take the value 1 if we have the failure observed failure time, and it should take 0 if it is censored. So I have R failures. So one is failure, another is not failure, one is failure, another is not failure. These are the values of delta. And when I'm going to take the summation of delta, so I will add all these values up to the nth value of delta. Yes or no? That's how I will add, yes or no? So if I have the R failures, so what it will be? I have the R delta i's with value 1. Other will be 0. So what is the R basically then? R will be summation of delta I of the all observations, because remaining which are not observed, they will be 0. So I have the 1. 1 will occur R times. So I will add all of them. So that will be R. Yes or no? So that's how I define R is equals to summation of delta I. Okay. Because we don't know which observation was failed. Okay. Which valve was failed, which valve will survive. We don't know that one. All right. So it denotes the number of uncensored failure here R. All right. And then how many censored will be there? How many censored value? If R is the failure, how many censored will be there? Right. N minus R censored observation we will have. All right. Then what is the expectation of Xi that we were finding in the beginning? Here, this one. So what will be expectation at that time? Expected value of Xi, sorry, expected value of summation Xi over the range of I goes to 1 to n, observed data at the tth iteration value of lambda. So it will be, how many observations you have? You have the over the range of I, delta I, yi is the observed data set you have, plus how many uncensored you have? N minus R into C plus 1 upon lambda t. That will be your expectation. Okay. Because N minus R is your censored observation. Number of censored observations are N minus R, and observed observations are yi, and y are those where delta I is basically equals to 1. It is equals to 1. Okay. So what will be your E step then? Q lambda t will be what we had, n log lambda minus lambda inside the bracket summation over the range of I, delta I is equals to 1 yi plus n minus r c plus 1 upon lambda t. That will be your expectation, conditional expectations part. All right. Now you need to find out the m step. maximization. All right. We need to maximize this one. Okay. How we will maximize this? We need to find out the derivative with respect to the lambda. All right. Derivative with respect to lambda. So of lambda of q, lambda t, what it will be? N upon lambda plus so this one you need to find out with respect to this. So it will be, sorry, it is minus lambda will vanish, only summation I semicolon delta I equals to 1 yi plus n minus r c plus 1 upon lambda t will remain. We will not do with respect to the lambda t. Why? Yeah, this is the given value at the tth iteration, right? So this is the given value, this is the known value. So now to maximize this, what you need to do? Put equals to 0, right? Delta I yi plus n minus r c plus 1 upon lambda t, and then put it equals to 0. Now solve it. So what it will be? The final solution. This lambda that you will get, that will be the lambda at t plus 1th iteration, right? So lambda t plus 1th iteration. So you will take this term on this side, on the right hand side, and it will be 1 upon lambda. So you need the lambda. So lambda will go in the multiplication in the right hand side, and this term will comes in the denominator part. So it will be n upon summation I for the delta I yi plus n minus r c plus 1 upon lambda t. Okay, this will be the solution at the t plus 1th iteration. Okay, so this is your qth part. Now you need to find out the observed data likelihood. What will be the observed data likelihood here? That will be the complete one that we assume in the beginning. This one that we solved for the complete data set. But our data set is not complete. It is the censored. So what is the likelihood under the censored observation? What is the formula to likelihood? The formula of the likelihood is basically under type 1 censoring, likelihood is basically of the lambda of x and c. It will be proportional to multiplication product of your PDF up to the n. All right, up to the n of your fxi for the yi, that are your observed data set. For the observed observation, raised to the power delta I, okay, for the observed data set into the survival function at time t. Value of x will be c because that is only you have, and raised to the power 1 minus delta I. Okay, that is your likelihood. So what it will be? It will be product of I goes to 1 to n lambda into e raised to the power minus lambda yi, right, raised to the power delta I, means for the observation 1 into what is the survival function, e raised to the power minus e raised to the power minus lambda c, because what is the survival function, e raised to the power minus lambda x, e raised to the power minus lambda x. But here we have the observation c for the remaining observations that was failed after working after the time c. So we have the only observed information about them, that is c only. So raised to the power 1 minus delta I. That is the likelihood under type 1 censoring. Okay. So what will be your log likelihood then? So log L will be sum of over the range of I delta I log of lambda, because lambda raised to the power delta is there. When you will take on the log of lambda and you will multiply, so I is applying on the delta. So that's why it will be sum there. There will be a sum of delta I. Okay. And log of lambda. Are you getting this point? Minus what it will be? Lambda summation of yi. Right? Summation. It will be summation of I over the range of I where delta I is equals to 1. It is applicable for when delta I is equals to 1 and yi plus apply here. So it will be 1 minus lambda. How many 1 minus lambda will be there? N minus r. N minus r into c. Okay. So that is your log likelihood. Now how will you find out the MLE? If this is your likelihood, differentiate with respect to the lambda and put it equals to 0. All right. So find out the derivative with respect to lambda and put it equals to 0. So what you will get? Summation over the range of I delta I divided by lambda minus summation over the range of I for the given values of equals to 1, delta I equals to 1 yi plus n minus r c. Put it equals to 0. What you will get here? What is your summation delta I? Basically r, number of failures, right? So that will be r divided by lambda MLE divided by summation over the range of I such that delta I equals to 1 yi plus n minus rc. Okay. Here, if you notice one thing, your MLE is in the closed form. Yes or no? If you know the values of the failure observations, how many failure observations are there, and the time of those failure observations you will put here, and total number of observations you have, and you have the C, value of C definitely you will have. At what time you are going to terminate your that one experiment. So you will get the MLE directly. So you don't need the EM algorithm. If you see here, because your MLE is in the closed form, right? MLE of the lambda is in the closed form, so that's why you don't need the that one EM algorithm. But this is why I took this example, because what happens in many distributions, what happens, the MLE is not in the closed form. So how will you estimate at that time in the censored observation? If you just see, it is little bit complicated somehow, little bit, because n minus r is there, number of observation that I observed there, that is C is there. All right, only lambda is not, means only y is not there. Okay, you have the other things also there. So if you are going to include other censoring schemes that are little bit complicated, like progressive censoring or hybrid censoring, or we have the some advanced censoring also, like progressive type 2, progressive type 1. All right, like that censoring schemes we have, or hybrid type 2 or hybrid type 1, like that we have the censoring schemes. So if those censoring schemes you will include, as well as you will include the some complex distributions like gamma. In the gamma, when you find out the MLE, you have the digamma function. If you remember, do you know that the digamma function is there involved in the MLE? When you, if you have the that one, what we said, gamma density. So in the gamma density, you have the alpha raised to the power of beta, gamma beta. If I am finding the derivative with respect to the beta, if I want to estimate the parameter beta here, so I need to find out the derivative of this one. What it will be? D beta of gamma beta. What it will be? This is called as the digamma function. Okay, you cannot solve it. So how you will find out the estimate? It will become more complicated. So at that time, EM algorithm or these techniques help us, iteration techniques, to find out the MLEs. I think time's up, right? Okay, so remaining things we will do, we will solve it in the next class, and we will do the R coding, and we will do in the right censoring and type 2 censoring also, and then it will finish. Okay.